What is the electromagnetic spectrum? The range or span of frequencies of electromagnetic radiation is called the electromagnetic spectrum. The electromagnetic spectrum is a way for scientists to classify different frequencies, thus photon energies, and their relative functions. Let's take a deep dive into the different regions of the electromagnetic spectrum. But first, let's briefly review photon energies. Electromagnetic radiation, or light, is a means by which energy can travel through space. The energy is equal to h nu, where h is Planck's constant and nu is the frequency of the light wave. These particles are called photons, or quanta. You can watch my previous lecture on Planck's work for a more in-depth discussion. Notice how the photon energy and frequency are proportional. Higher frequency means higher photon energy. Going from left to right on this example spectrum is increasing frequency, thus increasing photon energy. But recall, the speed of light is equal to lambda nu. Rearranging to solve for the frequency gives the equation c over lambda. Therefore, the frequency and the wavelength are inversely proportional. We can substitute this equation into the energy equation and rewrite the equation in terms of wavelength instead of frequency. Let's go back to the spectrum. While frequency increases from left to right, the wavelength increases from right to left, the opposite direction of the frequency. The range of frequencies and wavelengths in the known measurable spectrum is enormous. The frequency span is from 10 raised to the 4 inverse seconds to 10 raised to the 20 inverse seconds, some 16 orders of magnitude. And there are some textbooks that report even slightly larger spans. These frequencies correspond to wavelengths of about 10 raised to the minus 12 meters to about 10 raised to the positive 4 meters. The regions of the spectrum are divided based on the methods used to detect the different kinds of radiation. It is important to note that there is no definite border between regions, where one ends and another begins. There is small overlap between regions. Let's discuss those methods and the different regions of the spectrum. I'll start in the middle of the spectrum, the visible region. The visible region of the spectrum ranges from about 700 nanometers to 400 nanometers. This corresponds to a frequency range of about 4 times 10 raised to the 14 inverse seconds to 8 times 10 raised to the 14 inverse seconds. This is a very narrow range compared to the overall electromagnetic spectrum. Humans can see visible light, or photons. Photons of visible light are associated with the changes of electrons in energy levels within an atom. You can see my video on the chemistry of fireworks for an explanation. To the left of visible light, there is lower frequency, lower energy radiation. Infrared radiation, or IR, cannot be seen by humans, but we feel it by the fireplace as molecules in our body absorb infrared light. See, IR is associated with the vibrational stretching of molecules. Thus, molecules in our bodies absorb the energy of the IR photons from the fireplace, and our body temperature increases. Microwaves are associated with molecular rotations, and yes, this is how a microwave oven works. Water molecules rotate on their axes at a frequency in the microwave region. Microwave ovens bombard the water in food with microwave radiation, and the water molecules absorb this radiation, thus increasing in temperature. Then, at the lowest frequencies are the radio waves, which are associated with electron and nuclear spins in magnetic fields. We are all familiar with radio signals, communication towers, and cell phones. But did you know that radio waves are used for medical imaging? MRI, or magnetic resonance imaging, uses these radio waves to produce non-invasive imaging of tissue in the body. Now, let's go to higher frequencies. Higher frequencies mean higher energy of radiation. Ultraviolet, or UV, is associated with the changes in the electron distribution within an atom or molecule, as do X-rays. Gamma rays are very high energy and are associated with nuclear change. The reason these types of radiation are dangerous is because of their very high energies. These photon energies can range from 100,000 to 1 million kilojoules per mole. Chemical bonds, you see, usually range from 300 to 500 kilojoules per mole. Enough exposure to these photons can break chemical bonds and thus damage cells in the body. We can protect ourselves from UV by using broad spectrum sunblock lotion. Sunblock lotion contains large organic molecules with chemical bonds that absorb UV photons and disperse the energy throughout the molecule. Doctors and dentists' offices use lead vests to protect against X-ray exposure. Low dosage and infrequent X-ray imaging is very safe. Gamma rays from nuclear material should be disposed of safely, usually underground. And thanks to our atmosphere, we are generally protected from these types of radiation originating from interstellar space.